So here we'll check out number 2 from the 2013 BC exam, and this is a calculator problem that involves polar graphs, and we want to find the area that is shaded over here. So they tell us what the equations of these polar curves are. So r equals 3 is going to graph the circle with a radius of 3. R equals 4 minus 2 sine of theta is going to graph this limacone here. And they were nice enough to tell us where these curves intersect. So this intersection point right here has a theta value of pi by 6, and the radius has to be 3 since it's on the circle. So that ordered pair in polar form would be 3 comma pi by 6. And then this intersection point over here, it's also on the circle of radius 3, so the radius would be 3, and the theta value would be 5 pi by 6. If we want to find the area of the shaded region, you've got one of two options. In this video, what I'm going to try to do is I'm going to try to find this area by finding too little area and adding more area to it in order to get the area that's shaded here. So what I notice is if I draw lines from the origin to those intersection points, below that set of intersections, I have a circle and I have a certain part of the circle traced out. So if I redraw that, what I'm going to say is well, this is a sector of a circle. And if I want to find the area of a sector of a circle, all I have to do is I have to use the formula for the area of a sector of a circle, which is 1/2 times the angle of the circle that you're tracing out, which will be specified generally as theta, and then times the radius squared. So if I want the area of this, all I have to do is take 1/2. I'm going to have to do a little bit of work to figure out what theta is, and then my radius is 3, right? That circle has a radius of 3. So now we need to figure out what goes in place of theta. So when we start here and we go around the circle to this point, how many radians are traced out there? Well, if we're starting at this line segment here, this angle on the circle is given by 5 pi by 6, right? Straight from the intersection of those polar curves. So we start at 5 pi by 6, and we go around the circle. We actually go past the 2 pi mark right here, and we go pi by 6 beyond the 2 pi mark, right? Since we end at this line, which has a theta value of pi by 6 at that intersection. So to get from here to here, it would be specified by 5 pi by 6 as the starting value, and then ending not at pi by 6, but at 2 pi plus pi by 6. Well, 2 pi plus pi by 6 is going to be 12 pi by 6 plus an additional pi by 6. That'll be 13 pi by 6. And so if we take the difference between these angles, that's going to give us how far around the circle, how many radians around the circle we went to get from here to here. So let's see, 13 pi by 6 minus 5 pi by 6 is going to give us 8 pi by 6 or 4 pi by 3. And so we're looking at 4 pi by 3 as that angle. And this will give you the area of the sector. Now we do still need to realize we don't have the area of the shaded region. We just have the area of everything below these two lines. We still need the area of everything above them. So what I'm going to do is I'm going to draw that down below here too. It's probably going to be a pretty bad version of it, but it'll do what we need it to do. We know what this point is in polar form, and we know what this point is in polar form. Now if I want to find the area of this, I know I have it drawn like a triangle, but it's definitely not a triangle. What I want to do, anytime you're doing an area calculation in polar form, you want to use sectors. So I'm going to draw a sector that begins at the pole. And the area of this one sector right here can be approximated with 1/2 times whatever the angle is times the radius. Well, the radius right here, it's not a fixed radius, it's a radius that changes depending on what angle we sit at, but on this graph right here, on this limacone, r is specified to be, the radius is specified to be 4 minus 2 sine of theta. So we're going to have 4 minus 2 sine of theta here. And the radius, when you find the area of a sector of a circle, just like we had it back here, has to be squared. Now this angle is a little tricky because it's not that big of an angle. It's a really, really tiny angle right here that I have within the sector that I've drawn. I'm just going to specify it to be delta theta. This formula will get me the area of one of these sectors at whatever value of theta I sit at. What I want to do is I want to add together a bunch of those sectors' areas, and I want to use the definite integral to add together a bunch of those sectors' areas for me. Say that a few times fast, and it gets kind of difficult. So I'm going to integrate this expression here. The delta theta is going to become a d theta. When you do an integral, the delta x, the delta y, the delta t, that becomes the differential that tells you the variable of integration. So we're going to have to do this integral with respect to theta. Oops, and I forgot my exponent on r here. And if we go ahead and think about what the limits of integration need to be, what values does theta range between if all possible sectors that I could have drawn here range between this angle and this value of theta? Well, we know the value of theta right here is pi by 6, and we know the value of theta right here is the theta from the other intersection point, which is 5 pi by 6. So if we do this integral from pi by 6 to 5 pi by 6, we're going to have our result. This is a calculator problem, so I'm just going to get everything ready to go in my calculator here, and we'll talk about the result in just a second. So I got everything typed in my calculator here. Since it was a calculator problem, I definitely took advantage of the calculator's ability to evaluate this for me. So I used on the TI-83, the function integration feature from out of the math menu. So I typed in the integrand, comma, variable of integration, comma, lower limit, comma, upper limit. I got this value for the area of this region, and then I added to that the area of the sector of the circle right here, which gives me a total area for the shaded region, the part below found with this calculation, and the part above found with this calculation gave me a total area of, if you round that to 3 digits beyond the decimal, and there it goes. So what, 24.709 if you round that to 3 digits past the decimal. If you truncate it, if you had 24.708, that'd also be good. If you had 24.71, unfortunately, that wouldn't get you full credit on the AP exam.